We're happy to meet today, maybe for this second or possibly first time for a colloquium in this hybrid mode. And we're happy to have today Giulio Tiozzo from the University of Toronto, who won the André-Aisenstadt Prize for 2021, together with Thurston Collins. And Giulio studied first at the Scuola Normale Superiore di Pisa, and then he did a PhD at Harvard that he finished in 2013 with having as advisor Curtis McMullen. And he was a Sloan Fellow from 2018 to 2020. And he works in dynamical systems, in complex dynamics, random walks, ergodic theory, and Teichmüller theory. And he's considered a leading young mathematician on these fields. And he obtained some important results discovering connections between the Mandelbrot set and continuous fractions, and also showing that a non-elementary random walk on the mapping class group takes Teichmüller geodesic. And he will talk to us today about entropy along the Mandelbrot set. And we're very happy to welcome him, and we're very happy he came to visit us.
Okay, thank you. Yeah, so thanks very much for the introduction and the invitation. And it's really nice to be somehow back in giving seminars in person, even though this is still kind of a hybrid mode and lots of you are at home and watching. And so welcome everybody. And of course, I'm honored to have received this prize from CRM. So that's great pleasure to be here. Okay, so let me start sharing the screen. So I have a presentation. And so the topic I want to discuss today is various incarnations of entropy, especially in complex dynamics. And in fact, a lot of it will be a relation between real and complex dynamics. And so I will start with some introduction to entropy, just in a general sense. What is entropy in dynamical systems? And in fact, I think it's even more useful to think of the origins of entropy in dynamical system, not just coming from physics, of course, Boltzmann and these people, but also coming from information theory, like people like Shannon. And so I will start, in fact, with a brief introduction to entropy in linguistics. And then I will describe this entropy that Bill Thurston, in the last years of his life, started looking at, which is called core entropy. And I've been able to work with develop more of this theory and show some of the hypotheses that were thought of by inventors. So okay, let's start the game. So here's the game. So you're a spy, and you try to intercept message. The sound issue. Even closer?
No, lower a bit.
Lower a bit?
It was crashing.
Is it too loud? Is it fine right now? Let me see.
It's hard for them to know, but I'll check.
Someone says it's better. Yeah. Okay. Right. So the game is played like this. So you're a spy. You try to intercept some message. But of course, the enemies are not so stupid. So they encode your message. And how do they do it? Well, in a relatively simple way. They just switch letters for numbers. So you think of it, you receive the sequence of numbers. And then you want to know which one is the message and which one is the noise. So here's the two options. This is text A, and this is text B. So anyone in the audience, do you have a guess? So there's 27 characters in the English language and 27 numbers. So that's just simply what the coding is. But of course, you don't know which number corresponds to which letter. There's many things you can do, but just a wide guess from the audience. Which one? Who votes A?
A.
Just vote A or B? A. Andrew Granville votes for A. Okay, so let's take that. So this one vote, so that's enough for our democracy today, because it's kind of complicated to handle it. So let's see, what can we do to figure out what's going on? So, well, one idea that gave the beginning of information theory is that natural languages have redundancies. So for instance, if I give you this text, there are lots of characters that are missing, and you could guess from which book this is from. So this famous beginning of the picture of Dorian Gray. And you see that even if you don't know all the characters, you can still more or less read it. So how do we quantify this fact that natural languages have redundancy? And so this is the idea that inspired Shannon in 1948, who wrote this mathematical theory of communication. So he wants to say the following. So not all sequences of letters are possible, because this is not a random message. Certain combinations of letters don't arise in the natural languages. And so what he thought about is, okay, how about we count? What are the subsequences that can arise? And we compare to all possible subsequences. There are more sophisticated way you can introduce probability measures. So, okay, but this is just a very simple way you can think about. You look at all chunks of length n, and you count how many possible subsequences there are. So we have notion of entropy. And so if we do it for text A, we get 2.5. And I think here I took a logarithm in base E because we're mathematicians, but computer scientists usually take a log in base 2, but okay. And text B, you get 3.06. So now which one do you think is the natural language signal? Is it A or B? Some people in the audience say A. Anybody else? Anybody wants to say B? Let's see from the chat. More people say A. Yeah. A. Lots of people say A. Yeah. So in fact, it is A. And the reason is, well, I mean, that's doesn't need to be this way, of course, but experimentally, of course, you want to say that the natural language has more redundancy than just a random language. And so there are fewer combinations that are possible. And so you would have lower entropy. And in fact, if you did a random selection of 27 characters, you would get 3.29. So the last one is kind of close to the theoretical maximum. And in fact, the first text is the famous last verse of Dante's Inferno. Hence, we issued forth to see again the stars. And then the last one is just random message. So this is one way that people started thinking about information in linguistics. And we will see that in dynamical system, we have a somewhat very close notion of entropy, which is very close to this one. Before moving to that, just keeping the introduction, I want to say that one thing you could try to do, and people have done, this is definitely not my field, but people in computational linguistics, for instance, they try to discern a language in which message is written by maybe measuring the entropy. And well, maybe here in Quebec, it would be interesting to discern between English and French, but you can't really quite do it because the entropy is pretty similar. Oops. But if you compare, say, with Chinese and other Asian languages, this is in the red sequence, these have much higher entropy. So this is, again, this is definitely not my field of expertise, but you could gather information about your signal by using entropy, even in more applied. Any questions about the introduction? So now let me go to more mathematical and into dynamical systems. So now let's start with considering dynamical system, very simple one, but one which I really like is just the f of x equals x squared plus c. So just if you draw it, just a parabola, c is a parameter. So it's a quadratic polynomial, function x. And we want to introduce some coding. How do you introduce the coding? Well, 0 is the critical point, is where the derivative vanishes. And so we have a partition. Either a point is before 0 or is after 0. And by iterating your point, we can produce a sequence. So here's what we do. So we start with a point like this one is to the right. So we associate the code 1 because it's to the right. Then we iterate this map. We produce another point. Now it's to the left. So we produce 0. And what else? So if you do the next iterate, we go to the right again. So we produce 1 and so forth. So now we get 0. And of course, you can keep going. And depending which point X you start with and how complicated your system is, you could have different patterns. Of course, you immediately see that if you have a periodic point, the code will be periodic. Is the converse true? Well, this is already an interesting question, but not what we're concerned with today. What we're concerned with is a global notion of entropy, of topological complexity. And what is the global notion is we pick all possible codes. So we pick all possible starting points. We fix our map. So we fix the parameter C, and we pick all possible starting points. And so we can compute for each starting point an infinite code. Maybe there are some ties if you end up really at 0, and then maybe you have to decide exactly how to define that, but that's just a subtle point. But you produce a bunch of sequences, and you count how many sequences can I obtain. And that's exactly one of the definitions of topological entropy. So I call admissible codes all the codes that are produced by this dynamical system, and I count how many there are. Of course, if the map was completely random, of course, this is not a random system, is a chaotic but deterministic system. But one of the ideas, of course, is that if it's a very chaotic system, even if it's deterministic, it's impossible to tell it apart from a random system. So if you could produce all possible sequences, you're going to have 2 to the n. So you're going to have log 2. Otherwise, you have a number which is a bit below that. So yeah, so the max you could get is log 2. In fact, this is achievable in this setting. And so you can have a number that associates the degree of randomness of this dynamical system. Another way of thinking about it is if I give you specify the orbit of a point to the first n steps, can I predict the n plus 1 step? If the entropy is small, it means it's easier to predict the next one. If the entropy is big, well, it means it's kind of unpredictable. Now, there are many other ways of thinking about this. So there's a sort of a geometric way, which is the following. We can draw the graph of this function. And this function is piecewise monotone. So it's decreasing and then increasing. So there are 2 laps. Laps means just a piece where it's monotone. And if I iterate forward this map, I compose the map with itself, you can get more and more folding. So for instance, if I do the second iterate, how many laps do I get? It should be easy. Someone for the chat. 4, that's exactly right. And now, what about if I iterate another time? How many do I get? In this case, you get 8, but it's not obvious because if I do another time, how many do I get? So of course, the theoretical maximum you could get is 16, but in this case, I think you just get 14. So you can keep going like that, and you can count how much topological folding there is. And that, of course, this is not the classical definition of topological entropy. You study in a course in dynamical system, you take the partitions, you take the pullback of the partition, you intersect. This is all very nice, but too complicated for a sort of colloquial lecture. But it's a theorem of Visirevich and Slank that for piecewise monotone maps, you can compute the entropy taking this number of laps. So that's equivalent, basically. Exactly, for 8, 14. So Mariam got it. Good. Okay, so now one more definition. So this is nice because it always exists. It's a limit of a sequence, and its sequence is subadditive for simple reasons. So the limit by just Foucault's lemma would exist. But can you compute it? Well, if you have additional structure, you can compute it. So here's one way the additional structure comes. If the map is postcritically finite. What does postcritically finite mean? It means that if you take a point and the critical point, you consider the forward orbit, this orbit is finite. So either eventually comes back to itself or enters in a loop. So in this case, you can compute because you can write a matrix for which usually is called the Markov partition matrix and so forth. So in this case, for instance, suppose you have a point which is as critical point of period 3. And so if you have 3 points in the critical, maybe we can even draw a sketch. So you have 3 points in the postcritical set. And so you can divide the interval in 2 pieces, A and B. And then you look at the picture and you see the transitions. So you look at, if you take A, the image of A is the union of A and B. And the image of B is just A. So you write a matrix, transition matrix. And if you want to compute the number of laps of this map, you take powers of this matrix and you look at the coefficients of this matrix. In this particular case, it's pretty easy. You get a very well-known matrix. In fact, what happens if I take powers of this matrix? Maybe someone knows. This is a very special matrix that you studied several times in your undergrad curriculum. So if you take powers of this matrix, it turns out you get just the Fibonacci numbers. And so what's the growth rate? Well, the growth rate here is the golden mean. Growth rate is measured by the largest eigenvalue. And of course, well, there's this notion of entropy with the log. So we want to take a exponential of that yeah, anyways, the log of lambda is the entropy, but okay, that's just a minor thing. Okay, so this has the advantage that you can compute it. So these are various definitions of entropy. Now, in dynamical systems, what we care about is not just studying one system at a time, but a family of systems. And one of the most famous ones is just a quadratic family. So we can call this variable either X or Z, because depending on whether you think of it as real or complex, at the moment it's still real, but it will be complex pretty soon. And C is a parameter. And this was at the beginning of the modern theory of dynamical systems, this famous work of Miller and Thurston that studied what happens to this entropy as you change this parameter. And so Miller and Thurston wrote a very famous paper in '77 studying this function, so the entropy function. And in fact, this is the original graph from their paper. Of course, computers, maybe they're not still as powerful as today, but already you could tell a lot about this function. So well, the parameterization is slightly different. It didn't use C as a parameterization. But in any case, as a function even of the parameter C, this entropy function is definitely continuous. It's monotone. However, it's not smooth. And also, it's not strictly monotone. So there are plateaus where the entropy is constant, like this one will be 1. Or this one is found. Waiting. They move down or something. Is that better? Better. Okay, thank you guys. Okay, so you see that this map has large plateaus. For instance, the entropy is 0 for a very long time, actually, to the left, and eventually gets to log 2. And in fact, even the fine structure of this is not so trivial. I mean, this function is not smooth, and in fact, I even worked on the Hölder exponent of this function. I will show you some result later. So even if this function has 40, 50 years. But what is the real topic that I want to talk about is, so this kind of question that Thurston came up with was, can we define such an object, such an entropy function for complex maps rather than real maps? So of course, the real maps are all fine. But the problem is that how do we define this map? So of course, you have a quadratic polynomial. Quadratic polynomial is a map of the sphere of Riemann. But in some sense, if you just consider the Riemann sphere itself, it's sort of too big because every point has exactly 2 preimages, or except for maybe 1 point. So if you count the preimages, you always get the same number. You always get log 2. It's not telling you anything about the parameter. So it's one way of thinking about it, but somewhat boring because you can't really do much. Okay, and so now we have to describe a little bit more in detail what we want to say, how to consider the co-entropy. And to do that, I need to give you some crash course in complex dynamics, hopefully be gentle, but some. So what do we study in complex dynamics? So the most famous protagonist of this field is the Mandelbrot set. So what is it? Well, you take this quadratic family, where C is the parameter, and we take all the parameters for which the critical point, which is 0, does not escape to infinity. So either 0 escapes to infinity or not. So if it does not escape, if it escapes to infinity, you color this parameter with a color like orange or yellow, depending on how long it takes to escape. And if it does not escape, you leave it black, and then you get this famous picture. Of course, the geometry of the Mandelbrot set is still one of the biggest open problems in mathematics, and I did not solve fully that conjecture, but we will discuss how this is related to what I'm talking about. So one thing we could do with the Mandelbrot set, even though the geometry is really complicated, it's kind of nice because we can uniformize the exterior. So the black part is very complicated, and the exterior is still complicated, but complex analysis tells us that if you have a simply connected domain in the sphere, it's biholomorphic to disk, so kind of trivial. So there is a uniformizing map, and we can introduce polar coordinates on the outside of a disk, and this map to sort of polar coordinates. So these are called external rays in the outside of the Mandelbrot set. Now, what is the real tricky problem here is whether this boundary map extends, sorry, not boundary, this map on the exterior extends to the boundary of the Mandelbrot set. And so basically, if we fix, so for each angle, so you see you have a polar coordinate. So for each angle theta, there is a ray on the side, and this gives you a ray on the other side. And the question is, if we go towards the boundary, is there a limit? If there is a limit, we say that the ray lands. And if this was true for every ray, this would be great. I mean, this is sort of the dream of every complex dynamics. Because, so in fact, this is the famous conjecture of Giulio and Hubbard. So in fact, they already proved already in '84, yeah, I was born, that when theta is rational, there is, so rational multiple of pi in that sense, there is this ray and this ray length. And the ray length at the postcritically finite polynomial. So it's kind of very nice what happens here. The problem is, what about the other irrational rays? And the conjecture, the big conjecture is for every ray, also the irrational ones, there is a boundary map. The map can be extended to the boundary, and everything is nice. This map is a continuous map from the boundary of the circle to the boundary of the Mandelbrot set. And if that was true, this would imply that the Mandelbrot set is homeomorphic to a quotient of the closed disk. And from then on, we could completely understand the topology of it, because we could have a model for it, which is just a quotient of the disk. And to do that, we should answer it's a locally connected. So that's why this conjecture is called MLC, Mandelbrot locally connected. So in fact, Thurston introduced this object, which is very fascinating object. It's a lamination of the disk. So what's a lamination? It's a union of chords. We can draw them as hyperbolic geodesics inside the Poincare disk. So this is chords that join points on the boundary. And how do we join them? Well, we join points such that the corresponding rays land together. Because you see, the Mandelbrot set really is not a disk. So there are identifications on the boundary, and we want to record the identifications. So for instance, in the Mandelbrot set, you see, if you have this sort of stylized picture, so here you have a sort of the main component, and you have here, you have this bottleneck. So you have two rays that land, one on the one side and one on the other, and they correspond in the lamination to this chord here. So you want to record how to do these identifications. And once you do all these identifications, you get some toy object that you hope is homeomorphic to the Mandelbrot set. And this precisely, the content of the MLC conjecture is precisely that if the MLC conjecture is true, this model is a faithful model. You can completely understand the Mandelbrot set. This procedure. Okay, so this is sort of the main questions in complex dynamics, and what kind of is related, but of course does not quite address this main conjecture. Any questions so far, maybe? Or yes? Maybe you need the mic. Sorry.
Thank you. I didn't quite understand. Is it true that every ray ends at a point?
Right. No. So every rational ray. So,
okay.
So for an angle that is a rational multiple of pi, you know that this limit exists. And it's conjectured that for every ray, there is this limit. But we can't prove it for all irrationals yet. But a large family, a large set of them is actually. So in fact, the set of rays that possibly do not land has Hausdorff of dimension 0. So there is this fact. So this is just by complex analysis. So this set of possible counterexamples is very small. But in fact, we conjecture it should be empty. Yeah.
Thank you.
Yeah. Further questions or comments? Okay. So what comes next? So okay, the other object that people in complex dynamics study is a Giulio set. So one was the parameter space. This is sort of the dynamical plane. So for each system, we have such a set. And so the Giulio set, you've probably seen pictures of this. So basically you fix the parameter C, and you look at their critical point and see whether the critical orbit, you look at any orbit and see whether the forward orbit of a point is bounded or not. And you collect all points with bounded orbit, and this is called the field Giulio set. And then we consider the boundary of that is the Giulio set. So in many ways, the Giulio set has also other definitions, is the set of points in the sphere where the dynamics of your quadratic polynomial is chaotic in the sense that it does not obviously go to infinity, or it does not obviously go to a periodic point, or there are a couple of other things that could be rotation or something like this. But basically, this thin blue set is the set where complicated things happen for your dynamics. And so that's, of course, where we focus our attention. And the next thing that we need to do is, so the question is this. So remember, so we want to define a notion of entropy. So the problem is that we don't, in the real case, we have an interval. The real interval would be invariant by the dynamics, and you can construct and you can define the entropy. But in this setting, you have this fractal set. And if you consider the map on this blue fractal set, the entropy is too big, is always log 2. Even if you get rid of this whole outside of it, the entropy is too big. So we need a core, we need a smaller subset, which is kind of an interval. But instead of an interval, it will be a tree. So that's the notion of Hubbard tree. So what is the Hubbard tree? So you take the critical orbit. So you have the critical point maybe is at 0. And suppose maybe that the critical orbit is finite. So you have just finitely many mark points, which are given by the iterates of the critical point. And now you can connect them. You want a convex hole in a way that you can connect them by arcs that stay inside the field Giulio set. So in fact, there is some way to do that. And basically, the result looks like this. So there is a tree. This tree contains all the critical orbit. And it's convex in the sense that it's a tree-like object. You can connect any 2 points by an arc. And then the last property that is nice about this, by definition, and this is invariant in the forward direction. So you can map this tree into itself. You cannot take a pre-image. This tree is not invariant by backward iteration, because otherwise you will recover the whole Giulio set, which is too big. So basically, the upshot that we have so far is that I have a map, and then I'm given a tree. And then you have a map of of a tree. So for each C, I have a map of a tree. And once you, and this tree is forward in. And of course, once you have a map of a tree, well, you could think of, you could take the entropy because you have nice, for instance, at least in the compact case. So you could take a nice, this is a nice dynamical system, you could take the entropy. And that's exactly what Thurston suggested to do, is you start with a maybe postcritically finite set, finite parameter, or even more, like any parameter for which the Giulio set is locally connected. And we can define what's called the core entropy, which is the entropy of this map restricted to this thing. And so then the question, and then Thurston started playing with this concept and started drawing pictures. And well, before that, maybe let's recall how would you do this in a somewhat simple case. This is the previous one for the period 3 real map. Let's do complex map. So here's an example of a period 4 complex map. So you have this tree, which has it's a Y-shaped tree. It has 4 subintervals, and you could record the transitions. You see A maps to B, B maps to C, and so forth. There's some folding near the critical point. Anyways, you could encode this dynamics by a matrix. And of course, you could take the leading eigenvalue of this matrix. And in this case, in that also the leading eigenvalue of this transition matrix, now on a tree, not on an interval, but it's the same. You could associate a number, and this number is the log of the leading eigenvalue would be. So this is a very, very important definition. So maybe we could stop if there's any doubts or questions about this definition. It's really important to. Also from the online audience, any questions or comments? Okay. Yes.
Is it always a finite tree? So
okay, that's a good question. So if you start with the postcritically finite polynomial, then you have just a finite set of marked points, and then you get a finite. Now there are more complicated cases where this becomes better. How is it? Okay, so I think, yeah, so if you have a more, you could have more complicated situations where this is sort of an R tree. It has countably many branchings. So this could happen. Yeah. And then it becomes non-trivial to say what the entropy is. But okay. So in general, so this is the map that Thurston played with when he drew this famous pictures, so that I will show you in a second. So what he did is the following. So you start with theta. Theta is a rational number. So remember that to a rational angle, it corresponds a map which is postcritically finite. So it's a complex quadratic map, but it's finite because this is a rational number. So the orbit is finite. And from there, you take this tree. So instead of FC, we can call it TF theta. And now we have this map on a tree, which is finite tree in this case, because everything is rational to begin with. And so you take H of theta is H of F theta restricted to this T. And so this is the picture that Thurston produced. And that's how, well, I was already working actually on, during my PhD, I was already working on entropy of other systems like continued fractions that Octo mentioned. And I came across, my advisor showed me this picture and I was like, well, but fortunately, since I had this background before, there were some things that I could understand because there are some similarities with these two problems. I will not talk much about the continuous fractions today, but so anyways, so here's a picture that Thurston drew. And so what is this picture about? So on the x-axis, you have the angle. So the angle goes from 0 to 2 pi or 0 to 1, if you look at multiple of pi's. And on the y-axis, you have the entropy. So, and so yeah, so you see that the entropy is very small at 0. It's 0, 0. And well, in a very non-monotone fashion, increases towards 1/2, where it's the maximum. And then, okay, it's symmetric. But of course, if you look at this in this way, this is very non-monotone. So it looks very irregular. So the first challenge, which is sort of the main principle we're looking at, so okay, you can look at just half of it, is can you see the structure? Can you see the Mandelbrot set in this picture? And since I've looked at this picture for a long time, the answer is I can, but I can, of course, you guys still are amateurs about this yet. So not yet. So the point is this. So the idea is that this picture describes the structure, the topological structure of the Mandelbrot set as it's like a CT scan of the Mandelbrot set, looking at it from outside. And so let me explain what I mean, and I will show you other pictures that will make this more clear. So let me draw a sketch of the Mandelbrot set. Of course. Need a little bit of complexity, otherwise it's not, doesn't make any sense. So okay, so what is that we're plotting here? So if we start at 0, we look at the angle at 0, which lands at the cusp of the Mandelbrot set. So this point corresponds to a parameter that has 0 entropy. On the other hand, if you go all the way to 1/2, you are to the complete left. So you are at this tip point. And the entropy here is the highest possible. It's locked. And you can see, in fact, in the middle, there is this real slice, which is what Milner and Thurston were focusing on. So this is somewhat contained in this picture, but it's not easy to see because what happens in between. So you're going around the Mandelbrot set from the outside. And for each number, so for instance, if I give you the number 1/7, you look at the ray, it lands here. And this ray lands at another point of 0 entropy. So if you go to 1/7, it looks like you will find that the entropy is still 0. And the same, if you go to 2/7, maybe you're going to go to another point of entropy 0. So okay, this is kind of a boring game, but in the middle, in between two zeros, there is in fact this sort of mountain. And this mountain is due to the fact that in between these two rays, there is all this structure in the middle. There are all this limb of the Mandelbrot set. And for instance, if you take, I don't know, 1/4, this lands a tip of the Mandelbrot set, and this tip has high entropy. So here is the first principle here. So maybe it's time to show you another picture if I am able to. Let me see if I can. So here's a picture. I also had a sort of an animation, but I had some technical issue. But in any case, so here is how plots of the core entropy as a function of the C variable rather than the theta variable. Then you see the Mandelbrot set. So you see that from above, you have this huge region, which is this purple region, when the entropy is 0. And the entropy is 0 in the main cardioid, and also in every component which is attached to the main cardioid through just a finite chain of components. Because this bifurcation, the classical period doubling bifurcation is not strong enough to increase the entropy. However, there are later other components which are far, I don't know, say take the airplane component, so much further from the main cardioid, where the entropy here is positive. So near the tip, the entropy becomes much larger. So you see that, for instance, if you look at the third picture, you have a picture that looks a lot, the profile, it looks a lot like the Milnor-Thurston picture, because it is the same, because you're taking just the real slice. So this profile that you can see, it's kind of very subtle to see, but if you examine it very closely, you see that it has indeed the same, it is the same function that I showed you in the previous. But then there are generalizations of this. Every time you go towards, you know, from the center towards the outskirts to the periphery of the Mandelbrot set, the entropy is increasing. So that's a basic phenomenon. So let me be more precise, because maybe this is perhaps more confusing than anything else. So let's see. Yeah, this one. Okay. So right. So here's our precise results in this. Okay. So for instance, if you have two angles that give you the same parameter, so the two rays land at the same parameter, then the entropies must be the same. Well, this is obvious because they have the same, they're the same system. And the monotonicity still holds. What does it mean? It means that there is an order structure on your parameter, partial order, meaning that a point C1 is less than C2, or theta1 is less than theta2, if C1 lies on the arc between 0 and C2. So for instance, if you go from the center to a tip like this, well, you could take C2 to be, you know, the way we say it's C2 is up, is down here, 0 is here. So maybe if you pick a parameter C1, this is in the middle. So there is some partial order structure, and the entropy respects this order structure. And in fact, this is a theorem of, well, various people in various versions of it. The other thing is that the entropy determines the lamination, and it's kind of a nice observation that if you have 2 points with the same entropy, and every other angle in between has a strictly higher entropy, then these two rays have to land together, well, at least in a combinatorial sense. So basically, this lamination describes, is an equivalent to the entropy describes this lamination, and the lamination describes the topology of the Mandelbrot. So, okay, so maybe, yeah, maybe this is slightly tricky to digest. So, but maybe let's keep going, because there's many things to say. Okay, so another thing that I looked at, okay, so is what are the rays that land on the real slice? So on the real, so you see there's the real slice of the Mandelbrot set, and there's some rays coming from infinity land on the real axis, the ones that I drew here, for instance. Of course, many other ones don't. And you can ask this type of question, what about the harmonic measure? So what is the harmonic measure? Is the measure, you know, given by the push forward of the Riemann map. So in other words, it you know, answers the following question. Wait. Yeah, it answers the following question. If I come from infinity and I take a random ray, what is the probability that I land on the real axis? Or if I have some other set, what is the measure of the set of rays that land in some subset? And so the harmonic measure for the real slice of the Mandelbrot set has been studied already, and there's a theorem of Zachary. And in fact, it's extremely rare in a sense of measure to hit the real axis. In fact, the harmonic measure is 0. However, this set is not so small, because the Hausdorff dimension of the set of rays of the angles for which the ray lands on the real axis is 1. So it's a sort of borderline. And the reason is that this set is extremely inhomogeneous in the sense that if you go towards the tip, there is many, many more rays. And so somehow it gets fatter and fatter, and the dimension gets closer and closer to 1. And in fact, in fact, this is one of the results in my thesis. I generalized this in the following way, which is, can we take an intermediate parameter, and instead of looking at the whole real slice, can we take a smaller subset? And so here's what happens. So what I want to say is, I want to consider not the whole real axis, but just one parameter along the real axis. And I can take all the rays that land in between that parameter and, say, the cusp. So if I pick this parameter, I have this red segment, but unfortunately, there's very few rays that land there. There's only 3 rays. So this is extremely smaller set. But if I make it larger, now I get 5. Still small. But OK, maybe if I go further, I can get an uncountable set of rays. And this set of rays will have some dimension. And we know that if we go all the way to the left, we're going to get dimension 1. And if you go all the way to the right, we have dimension 2. So what happens? And what's kind of remarkable, and this is the principle about the Mandelbrot set, which has been going on, been around for a long time, is that the Mandelbrot set is very inhomogeneous, like many parameter spaces. And in fact, if you look at the Mandelbrot set near some point, you can see really the dynamical properties of the particular parameter where you're zooming in. And so this is a proved version of this, looking at this entropy. So here's what I proved. So I consider this function P of C. So I pick a parameter C, and I look at all the rays that land to the right of it in the real line. And I take the dimension. And this function certainly is between 0 and 1, and it's decreasing. What's the other function that is monotone? It's the entropy. And so what I proved that these two functions are the same. So on the one hand, you take a point, you take its entropy, and OK, you have to normalize by these two. Additional skill needed for this. Better? Yeah, maybe it's because it's the shirt or something. Maybe it touches something. Anyways, so hope is it better? Yes. Okay. Thanks. Yeah. So on the one hand, you have a dynamical property, which is the entropy of this particular parameter. On the right-hand side, you have a property of the parameter space. You're cutting the parameter space in certain point, and you look at this image. And what I prove is this same function. And so you can compute one in terms of the other. And it's kind of neat also because, well, the similar theorems, there's a relation between entropy, dimension, and Lyapunov exponents. Here, the Lyapunov exponent is the log 2. So in general, there's formulas like Redropier-Young formula and so forth, where you have entropy divided by Lyapunov exponent. This is house of dimension. Log 2 here, because this is the Lyapunov exponent, or just a doubling map on the circle, because you kind of trivialize that part. And what's kind of neat is that we don't know the local connectivity conjecture, but we know that the rays that don't land, there are not so many. The dimension of them is very small, so it doesn't hurt us. Yeah. Also, people studied another object, which is the set of bi-accessible angles, so which is related to the, basically it's the measure of the boundary, the intersection of the lamination with the boundary. And people have studied the dimension of that. And in fact, this entropy is also equal to that. So somehow you can also be interested in that. And also, I noted that you could generalize this to non-real veins. So in fact, what you could do is you could take another parameter, non-real parameter, for instance, 1/4 or something up here. And you have a notion of vein, meaning it's a segment that connects you to the center. And then you can play the same game. You can say, take all the rays that land on the vein. And again, it's the same thing. So you cut your Mandelbrot set at some point. you look at that point. This point has an entropy, in this case, the core entropy. And on the right-hand side, you take this rays that land in between the point you cut and the center, and you take the dimension of them. And this, you have this equality for, well, I did it for certain veins, and then Wolf-Jung also extended it to more general veins. But anyways, this principle still holds in general. Okay, so this is the first thing that we could do with the core entropy. The other question that came about was the question of continuity, and this came about with the famous bet between Thurston and Hubbard, where, because Thurston gave this seminars at Cornell around 2010, 2011, and there were a couple of people in the audience, and so he was just sort of lecturing without, you know, there was no many proofs, but lots of ideas, as in the usual style. So one question that came about is this continuous, and of course at the moment you could start with defining it for rational angles, and you know, it's very fractal and very complicated, but what I proved is that indeed this entropy function extends to all the irrationals, even though we don't know all the rays land, but we still can define the entropy for irrational angles. And that's also a nice construction. It goes to infinite graphs and stuff like that, which is quite yeah, I don't have time to say, but the next thing is that not just the continuity, but the quality, the regularity of this function is extremely interesting and extremely related to the geometry of the Mandelbrot set once again. Because, well, first of all, the entropy is not Hölder where it's 0. So it's continuous, but not Hölder. So it jumps very brutally at this point where it's 0. However, it becomes more regular. When the entropy is higher, it becomes more regular, and the Hölder exponent improves as you get closer and closer. In fact, I proved the following, at least for the real cases, but they are basically true in general. So there's this very strong property that if you look at this map, this function, and you look at the local Hölder exponent at the point, this is equal to the value of the function. It's pretty remarkable property. Yeah, so you see that this entropy becomes more and more regular. As the entropy is large, in some sense, it's a sort of stochastic stability. Like if the entropy is 0, it's very easy to perturb and create larger entropy. For instance, you can think of it in terms of hyperbolic set. It's easy to construct hyperbolic set with positive entropy if you have no entropy. If you have a lot of entropy to start with, the system is more regular in this sense of stochastic regularity. So it's harder to perturb. When you perturb it, it's harder to produce even more entropy. I think this is a general phenomenon which should be maybe more invested. I don't know if it comes up in other fields in mathematics, but it somehow seems kind of general in some sense. So this is a strong property. Yeah, it turns out that there's an older paper by Isol and Politi where they more or less made this conjecture, which is okay, maybe slightly forgotten by the time I came across it. But eventually, this is strong property, even for the reals, which has been studied since Milner and Thurston. This is new. Okay, so let's see. So I have still maybe 7 minutes around. Yeah. Okay, so now there's various directions, of course, one can go. So one other very nice thing is where are the maxima of this entropy function? So in the quadratic case, for instance, well, and this idea really came from this work the series of papers that I wrote about continued fractions with Carlo Carminati, because we had this idea of whenever you have two points, so any two numbers, you have an interval, and you can define their pseudocenter. So what is the pseudocenter here? Well, it's a very simple concept. It just is the dyadic rational, so the number of form p over 2 to the q of the minimal complexity. So the denominator is the smallest, and it's always unique. By the way, the way it's defined, it's always unique, because if they have two of them in the between, there will be another one with even smaller denominator. So yeah, so it's a unique number, and this number in many dynamical situations is quite quite natural because, so let's do an example. So let's say you start with 1/7 and 2/7. So what is the pseudocenter between 1/7 and 2/7? Here's an exercise for the audience. We have to consider dyadic numbers. Any takers? So the simplest possible dyadic number is 1/2, but this is not in the interval. So what's the next simplest? 1/4, yeah. And it turns out 1/4 indeed lies in between this interval. And so we could, so that's indeed the pseudocenter. But what's kind of nice, and exactly when I looked at these pictures that Kurt showed me in grad school, and Thurston, because Thurston was sending these emails to a lot of people, and there was a community of people that were trying to understand what these pictures were about. But I already worked on a similar concept, so I looked at this picture and I made this conjecture. So if you take 2 points for which the 2 rays land at the same dynamical point. So in the middle, so you have this strange graph, but you have 2 points that have the same entropy because the 2 rays land at the same point, and you look at the maximum here. And it turns out that the maximum really is achieved at the dyadic number of lowest complexity, so the pseudocenter. And in fact, so for instance, here's an example. So this is the graph of the entropy function on the right. So yeah. So here I highlighted 1/7 and 2/7. You see, so the entropy is 0, and you want to, and the maximum is here. And well, in this case, we know what the maximum is because we already did this exercise. So it turns out that the maximum is indeed the 1/4. And in fact, this conjecture was later proven by Dudko and Schleicher, Noah's theorem. So this is for quadratic. So now, maybe in the last couple of minutes, I want to show you what one could do in a higher degree. Because of course, quadratic polynomials are really nice and I really love them, but there are other numbers higher than 2, for instance, 3. So for cubic polynomials, you can still define the entropy. But the situation is even much more open. Like in general, for cubic polynomials, for instance, the conjecture that the analog of the Mandelbrot set is locally connected is false. So we really have no hope for that. But we still could prove certain continuity for recurrent. So the parameter space here, first I show you the pictures and I explain what these pictures say. So the parameter here is, here in the degree 2, the parameter was this angle theta, which lives in a circle. But here you have 2 critical points. So we have 2 parameters, 2 combinatorial parameters. And so the place where this function is defined is a 2-dimensional set. So it's actually a strip. And in some sense, if you think of it carefully, it's a Möbius band. So you could draw, so there's a larger thing, but there's some natural periodicity. So maybe you could draw it in this fashion. So this basically, so you see that you have 2 maxima. One is here, one is there. So these are already of different fashion. So, and also what you could do is whenever you have a high dimensional parameter space, you could take slice. For instance, you could take 1-dimensional slice ZQ plus C and has lots of maxima here. So this is I don't really know exactly what happens here. The other case is if you take ZQ plus C times Z, that's very much more similar to the actual quadratic space. So what we did prove, well, first of all, here again, it's really non-trivial. And in fact, this is the very last paper of Thurston. And in fact, not just Thurston, because this is an incomplete paper, but then these people that worked in the Cornell seminar, Weigel, Hubbard, Aisenstadt, and Thurston, Thurston the son. So they completed this paper, and it's been published. But even already to construct the combinatorial parameter space, which is no longer a circle, is a bit more complicated, and we call this the space of primitive majors, because it's basically in degree 3, it's the space of combinatorial objects of this form. So either you have two chords or you have a triangle like this. And because on the left-hand side, this corresponds to having two distinct critical points. On the right, we could have one critical point as a limiting case. And so the parameter space has already complicated topology. And in fact, its fundamental group, this is the last theorem of Thurston, is braid group in these strands. So for 2, you get Z, B2. But already for 3, you have this Möbius, it's like a 3. This parameter is like this. It's like an annulus. And you take the inside of the annulus and you wrap around itself 2 times. And the outer circle of the annulus, you wrap around itself 3 times. So the fundamental group has, for instance, this presentation, and it's already non-abelian, very interesting group. So this even already just that is a highly non-trivial. And then we considered with Gaussian, we considered this continuity problem, and we could also do it in higher dimensions. So basically, we also proved that we can extend this map on this space of primitive measures in a continuous fashion, even in high. And in fact, also we have a combinatorial, this would be the combinatorial condition. And also in the analytic sense, well, it's maybe even more natural if you have complex polynomials, you can control the coefficients. And you could ask whether if the coefficients converge, does the entropy converge? And it's sort of a corollary of the previous one. I mean, not completely trivial corollary, of course, but we could see that this co-entropy function also is continuous. Okay, so I basically out of time. So okay, there's some questions that maybe we could discuss if there are some interest later. So we had this transition matrix. We have the entropy is the leading eigenvalue, but people are also interested in general other eigenvalues, and Thurston was too. So what if you consider the other eigenvalues in transition matrix? And for the real maps, Thurston considered this. And in fact, he plotted this famous fractal picture. Now I'll conclude with this one. In fact, yeah, I've been working a bit on this picture too. For instance, proving it's connected, but so this, of course, would be a complete another talk. Anyway, thanks very much. Proceed.
Thank you very much. So, are there any questions?
I have a question. In these results, you seem to have used the uniformization and like a biholomorphic maps. So to what extent do these results generalize to dynamical systems where there is no complex analytic structure?
Yeah, that's a good point. Well, ultimately, what they really use is the underlying combinatorial structure. And so in some sense, so the uniformization theorem is a nice way to go from the analytic structure to combinatorial structure, which is this combinatorial structure of the doubling map, and you take a certain laminations. And so in the end, the theory is not as analytic. So you could consider systems that have a nice combinatorial structure. But of course, if you just start with a smooth system where there is no complex analytic structure, you cannot relate to the smooth structure with the combinatorial structure. So maybe so certain things you could say, but it's kind of would be different.
Thank you.
Thank you.
Any other questions?
Hi. So maybe I have a question about when entropy is 0. Is there some sort of reasonable slow entropy and something that can be said about it?
So you want to you would want some other notion. Yeah, that's a good point. Yeah, so first of all, I mean, the entropy 0 phenomena here is related to maps which are kind of well understood because they're basically given by the classical period doubling cascades. So in that case, really you have this periodic cycles that's the double, and so somehow like until the limit, which is the Feigenbaum map, you have very nice finiteness property. So it's very slow the entropy. Of course, the limiting point is the Feigenbaum, which has already very interesting non-periodic combinatoric. So I assume maybe this might have been studied from that point of view. So I don't know if there's really any real intermediate step which is so interesting in that sense. But yeah, I don't know. That's good. It's a good point.
Thank you very much.
Yeah.
Okay. If there are more questions, please go ahead. From distance or from the room. So I don't think so. So let's thank Giulio again